All right, yes.
Yeah.
Okay, great. Yes, great. I'm Cornelia. I would like to talk about low power FPGA-SoC-based secure mobile robot architectures. So we use FPGA-based systems on chip on our mobile robot, and the system on chip consists of a CPU with 4 ARM cores and hardware accelerators on the FPGA. So for hardware accelerators, for example, we use object detection so the mobile robot can move around, or it could be, for example, encryption cores. If, for example, the position needs to be encrypted for communication with another robot. So on the CPU, we run then our ROS, robot operating system. And if we now assume that the robot can move in an untrusted environment, we can have actually 2 versions of the operating system on the CPU. We can have a trusted version and an untrusted version. So in this case, we just would run 2 operating systems, which are managed then by a hypervisor. So for the hypervisor, we use L4RE. And on top of it, we can have our operating system. So we can have a ROS on top of Linux, or what we are currently doing is integrating microROS on FreeRTOS. The hardware accelerators are connected via a bus system. So we support the stream-based Axi4 stream accelerators. For Axi stream communication, the processor uses direct memory access, DMA, to communicate. So here we have already got a solution using virtual memory, which is then mapped to TDMA space. So here we have got memory isolation already. But what we are looking now into is the Axi4 Lite or Axi4 full communication, because this is a memory mapped communication, MMIO. So here, the tasks on the CPU can have direct access to accelerators only via a fixed assignment, or if we have got need more flexibility, we can use the hypervisor, which would look like this. Either we assign the memory mapped I/O regions in a fixed way to hardware, software tasks. So in this example, we could assign task 1 to accelerator 1. So we give the access rights only to this memory region. And in the example, we could assign task 2 to accelerator 2 and accelerator 3. But if now task 2 wants to use accelerator 1 as well, and we do it in this way, then this memory region would be considered as a shared memory. This means that task 2 can read the data of task 1 and vice versa. And this we actually don't want. So we can say at design time, we don't give the memory rights, but then it can't access accelerator 1. So this solution is not flexible and not scalable. The access rights have to be given at design time. A more flexible solution would be this, that we give all the access rights only to a scheduler in the hypervisor. This means that the tasks can only access the accelerators via this scheduler, which is working, but it induces some latency. So better would be a direct access to the accelerators, and that's what we currently are doing. It looks like this, that we have got the scheduler as a hardware module. Additionally to the scheduler, we have got a custom memory management unit, which is responsible for address translation. It's actually integrated into the Axi Lite communication, so it's put between the into the read and write address line. The scheduler is realized in VTIS HLS. If a task wants to use the scheduler, it would send the accelerator it needs and its priority to the scheduler. And this one sets then an entry into the translation table of our MMU. And this is done for spatial multiplexing, but we also do temporal multiplexing. So the scheduler can do some workload balancing. And also we have got priority queues for all the accelerators to determine which task can be executed first. And this looks then like this. So if task 1, for example, wants to use an object detection accelerator, it was first sent a request to the scheduler. This would then decide which accelerator it's allowed to use. and insert an entry into the translation table, which consists of the virtual address of the task and the physical address of the accelerator. So if task 2 now needs also an object detection, and we assume we are in an embedded area and don't have that much space, so we assume there is no second object detection accelerator on the FPGA, and we don't have the space to load another one. So we can also share the accelerators. And this would mean that the second task receives another address range within the address range of the physical address of accelerator 3. So this means we add an offset. Now, if task 3 wants to use an encryption core, it can just use one because we have here 2. So the scheduler would just do some load balancing for this one. This was the spatial multiplexing. For the temporal multiplexing, we add priority queues into each wrapper of the hardware accelerator. For access control, we use the I/O server from L4RE. This is actually like a daemon program that controls the access to the peripherals, and it uses a configuration file. This is an excerpt from this configuration file. So what you can see here is that the scheduler receives the complete access to the whole MMIO address range, and it also receives access to all the interrupts. So the tasks cannot use any interrupts on their own. The tasks do actually need 2 different memory mapped I/O regions, one to access the scheduler via Axi4 Lite, and the second for the virtual addresses. So each one has got one memory address range for the hardware accelerator, and it's important that they get different disjoint address spaces. So the second task gets one with an offset. And then they, of course, have their virtual address ranges, which must be disjoint as well. So now if software task 1 wants to use an accelerator, it sends the request to the scheduler by writing the accelerator that it needs and the priority to a certain address, which would be in this case the base scheduler address. And from this address, the scheduler can identify the sender of the message. So it's not possible to pretend to be a different task. The scheduler would then insert the entry in the MMU. And if now the second task also sends a request, it writes the accelerator that it needs and the priority to a different address, which is given by the offset. And from this, again, the scheduler can identify the sender at this entry. And then if a task wants to use the accelerator and there is an entry in the table already, then it does not need to contact the scheduler again. A periodic task can send as many task instances as it wants to use the accelerator without any further integration of the scheduler. So it just writes the data to its virtual address range. This is now translated to the physical address, and the parameters are written to a certain region. Then if task 2 wants to use the accelerator, it just writes its data to the virtual address 2. The parameters are inserted into our priority queue as well. And then the priority of the task decides which one can execute first. Advantages of this solution are that we can prevent unauthorized access. Shared usage of hardware accelerators is possible. We preserve the priorities. And we can reduce the latency compared to the software version. Disadvantage is, of course, each virtualization produces some overhead. Still, this is work in progress, so we can't evaluate yet how big the overhead is. As a future work, I just said that the interrupts are given all to the hardware task scheduler, but of course it would be possible to virtualize the interrupts as well. So currently the software tasks have to poll for the results, but it could be also possible that we interrupt signal, that the result is there. So we have got 2 students who are helping us with this project. These are both nanoelectronic systems project works. So one is doing the hardware task scheduler, and the other one is looking into the exploration of your security threats mitigation using microROS and L4RE. So that was our the state of work. Have you got any questions?
Did you talk to any robot manufacturers already to see if it could be implemented?
No,
Okay.
not yet. It's not yet in that stage.
Right.
But it might be interesting, I hope.
Yeah. I'm not sure how many that are using low power FPGAs actually to steer the robots.
Right.
Maybe something that we can find out also from here. Platforms maybe also have some robots running around. Okay.
So about that, right now not many robot manufacturers do, but there is a lot of interest in companies, and one proof of that is, for example, Silence is giving a lot of money to making their devices readily available for robot manufacturers and robot companies. They are producing now the FIA, which is a platform exclusively for robotics, but for consumer robotics. And now they, like 3 weeks ago, they launched a new SOM system or module, which is for industrial robotics. And it's a module that is also readily available for industrial motors and industrial robot applications.
Okay.
Yeah. So at least, and I mean, AMD is a big company, and they wouldn't do this if they don't know something. So yeah, there is some interest. The problem is that tools for using FPGA right now are extremely difficult to use. We see here we have a bunch of doctors, PhD students and doctors, and still we struggle to build it. And yeah, and so that's the problem mainly. But there is a lot of interest from robot manufacturers because of all the advantages that you like parallel processing, distributed processing, integration mainly. So far, the only robots that commercially have FPGAs embedded almost always are drones because of the sensor integration. They always,
Because of the workload also that's they need to play. Yeah, but for industrial robots, I haven't seen too many of them. So.
Yeah, but Silence 2 weeks ago launched a development board for industrial robots.
Okay, yeah. Okay, very interesting.
Why are the tools difficult to use? Is there a specific reason we just like related to? No, but that's the truth for everything. But the main reason really is, and this is something that a friend of mine that works in the UK for FPGA consulting, is that if you count the amount of elephants that you have in zoos and the amount of FPGA developers that we have in the world, we have more elephants. Yeah, I think it was elephants in zoos in the UK, even something like that. Yeah, so that's one of the main problems. But yeah, now with the reusability of chips, like 2 years ago, we had a huge chip shortage, and if people would use FPGAs, they wouldn't need to launch a new chip, but just update a bit stream, right, with the new architecture. And so now there are interest in that, revitalized interest in.
Yeah, true. But it could also be an interesting perspective for robot manufacturers, which have specifically been very slow in adopting security practices, and maybe also the supply or the lack of supply of the necessary tools in order to do that might also be a bit of the reason. But definitely also the lack of security engineers is a big issue.
So it's the reason that they did this work with HLS. There a specific reason why?
Well, it could be done with Verilog or VHDL as well.
Because beginning this discussion, like there are indeed not that much GDL developers with the computer more software world in HLS. So I was just wondering whether this was a deliberate choice to go for HLS.
Well, not really. It's yeah, it could be done with any HDL actually. Yes.
Yeah.
All right. Thank you so much, Ian.